Second question, solution of quiz. Shown below, in this case you see it in the figure, is a plane wave hitting a boundary. There's the boundary. The black stripes are the peaks and the white stripes are the troughs. The peaks are separated by a wavelength. So let's even between the whites, there's a peak and a peak here. In the transmission medium, down here, we are given the equation that you read in your quiz. Now, the first thing to do is label the materials in the figure above as supporting fast versus slow. So let's look at this. Here's a wavefront right here, like this, and here's my normal vector k. And that should be 90 degrees. So there's the k vector coming down. And let's draw the boundary right there. So not great, but there's my boundary. There's k coming down there. Now, what happens here is that we have to draw the normals to the wavefront. So here is a wavefront, and the k is normal to that. So normal, perpendicular there. So this is k1. And this is K2. Now we see that the K1 is at that angle, and the K2 relative to a local perpendicular is bent away from the perpendicular. And so therefore, this one is slow, this one is fast. Additionally, look, the frequencies of the waves have to be the same. So in one cycle, one frequency cycle of the clock, one wavelength in the lower medium takes this distance, which is bigger than the wavelength distance here to here. Since V equals F lambda, and F is the same in both media as we discussed in class, that means when lambda goes down, V goes down. So slow, fast. Does this picture model theta greater than critical or theta less than critical? Well, we have the angle of k here. It's critical means the wavefronts are going this way. That means the wavefronts are perpendicular. So this is less than critical. So B is theta incident, which is equal to theta 1, is less than theta critical. Now, next question is draw the same picture of crests and troughs when you're at critical angles. So I'll just sketch out what it's going to look like. It's going to look like this. Here are the wavefronts. And at critical, these guys are like this. So these are like the peaks. They could be like the black. And this distance is going to be smaller. So I didn't draw this quite right. This distance is smaller. Let me draw it again. These are bigger, so we have to, just there and there. So this distance here is bigger than this distance here. All right, so that's what it looks like at 90 degrees, and the amplitudes are the same all along these wavefronts. And that's a schematic answer for part C. Now, for part D, what's it going to look like? Well, we're beyond critical, so we have these wavefronts like this, and this distance is still bigger, except the amplitudes are not uniform down. They're not like they are here. We have exponential decay, so they're bigger and then they die away. Bigger and die away. So the profile of the amplitude is a decaying exponential, x being that way and z that way. That's D. Now E, use equations to confirm this. Well, we actually did that in the previous question because the transmitted field is proportional to e to the minus j cos theta 2x. That's what we found out. And this is minus j times some number. Call it j, so we get exponential decay. So there's a traveling part. E transmitted is proportional to this part, which is decaying, and then there's a sinusoidal part as well, because the wave is moving in the z direction. Now, F, amplitude in x, first part, decay. Sine wave in z. If we look here, you still have the fronts moving in the z direction, but decaying away in the x direction. So we have a sine wave motion in z. The wave is traveling in the z direction, and the energy is also in the z direction. And why is it in the z direction, in the positive z direction? Well, you could see that right near the interface, we have just this peak which matches, so the energy is going that way along the interface, but nothing is going down, and the answer is in the plus z direction. You don't have to compute the Poynting vector.